Good day, I'm Dr. T and welcome to my dining room table. So when we think about metal ions, we think about these guys being cations, and if these are in, say, an aqueous solution, we will typically think about these cations as kind of floating free, unattached. They're just kind of doing their thing. But that's not really the case. Outside of, say, like a hard vacuum where there are, ions in space or something, generally speaking, what you're going to have is small molecules like water or other ones such as ammonia, etc. Ones that have lone pairs. So if you think back to Lewis symbols, when you have a Lewis symbol, you have unpaired electrons. Those are typically going to be used to form covalent bonds. But you'll also have paired electrons, what we call lone pairs. And these typically don't do much. But one thing they can do is interact with metal ions. This is called a ligand bond when they're interacting, and the molecule that's doing the interacting with the metal ion is known as a ligand. Now there's actually a couple different ways they can do this. They're all kind of a covalent-ish nature of a bond, some more closely resembling a covalent bond than others. But in general, they'll just kind of be associated with the metal ion as it floats around. Now, in most cases, if that metal ion then forms a lattice and is incorporated into a solid, then those ligands are simply squished out of the way. They go away because those ligand bonds typically are not all that strong. They can be fairly tough, but not usually all that strong. It just depends on which metal and which ligand. However, specifically with water, we sometimes get a case where the waters surrounding the metal ion don't get squished out of the way when it forms the lattice. Instead, they get incorporated into the lattice. This is what we call a hydrate, and they're useful to keep in mind because they can have slightly different physical properties. And a little later on, when we start trying to keep track of atoms, we're going to count them by weight. Essentially, we're going to weigh whatever material we have. We'll know the average weight of the atoms, and with that, we'll be able to figure out how much we have. Well, those water molecules will be there, and thus we'll have to account for them. And thus, this is a way that we can do this. So we're dealing with hydrates. So let's start off with kind of a nice quintessential hydrate. Magnesium sulfate, heptahydrate. Okay, making that 2, not a Y. Okay, so what's going on with this one? So essentially what's happening is magnesium sulfate, aka Epsom salts, can co-crystallize with water molecules, and they can actually do a couple of different blends. So one of them is 7 water molecules. And in this case, what I'm going to do is name this just like I would normally. And spoilers, already gave you the name for this. But for this one, what I'm going to do is name him like normal, magnesium. Sulfate. Now, I am going to tell you how many waters are in this, because this can be any number. Obviously, certain salts will co-crystallize with certain numbers of water per what we call a formula unit. This would become the formula unit. It's kind of the repeating pattern within the lattice. That's called the unit cell, which I'm not going to get into. But this is kind of repeating, this is your whole number ratio. Okay, I'm going to call that heptahydrate. Okay, so magnesium sulfate heptahydrate. Now, obviously different things can have different numbers of them. Let's look at a couple of them. Long pen. So let's look at sodium carbonate. Na2CO3. And actually in this case, I can do this with 10 waters. And these are called waters of hydration. I can do this with 7 waters. I can do this with just one water. We don't typically put a 1 there. And for all of these guys, you can also have them without waters. So let's work through, and I'm going to show you how I name these guys. Fairly straightforward for doing this one. Okay, so it's just going to be the exact same pattern over here. So I grabbed the right spelling for the word sodium because I always get that wrong. Okay, so I have sodium carbonate, and then I will call this the Greek for 10, deca. Decahydrate. Now you can guess right up from that one, this is going to be sodium heptahydrate. This is going to be sodium carbonate, monohydrate. By the way, quick caveat, these are Greek prefixes, not Latin. So if you were to have a 4, it would be terra, not quattro. Okay, now here's actually the special case. So in this case, I want to tell you that it doesn't have any waters. It normally has waters, but in this case it doesn't. And I can get it in this fashion by heating it up quite often, driving the waters off with some good old-fashioned heat. So I'm going to say that this is anhydrous. An means not, hydrous means wet. And then sodium carbonate. So yeah, we have with varying numbers of waters of hydration, and then without any. That is the anhydrous. Naming these guys are fairly straightforward. When looking at the chemical formula, if you're going to be, say, doing a molar mass, then you would have to include the waters in that, and I'll get into doing molar masses in later videos. These are ones you do see on a fairly regular basis, but, you know, not a ton. So things to keep in mind. Now, not every hydrate is going to just stay the way it is. They can change, water can come and go. This is really more of a physical change than it is a chemical change, although it definitely is on the border between the two. So for most of them, you can convert a hydrate to anhydrous by simply sticking it in a low temperature oven, something around maybe 100 or a little over degrees Celsius. This way you bake them enough to get the water out of there. You just at or slightly above the boiling point of water. And for most of them, you can drive the water off in that fashion. Not all. Sometimes the hydrate's in there really good and tight. Now, for some of them, they'll actually lose that water. This is referred to as, and I'm going to butcher the pronunciation, elefluescent. I'll put the word somewhere on the screen. And these will spontaneously lose water to the atmosphere. Now, most of them are going to be the opposite. Most compounds that are hydrates tend to be hygroscopic. And hygroscopic compounds are ones that are capable of pulling water from the atmosphere and incorporating it in their crystal structure. This will cause them to change colors, potentially swell, do other rather interesting things. Not to mention, if you need the material to have an accurate weight, then this will create a problem. So for this reason, that's usually why you are strongly encouraged to keep the lid on the bottle when not in use. That keeps the water from getting in there just by keeping the air, trapped. By the way, this is how those little packets in your shoes and other properties work. The little tiny packets are called desiccants, and desiccators or desiccants are going to contain a hygroscopic material in them in order to pull in water. Now, there are some hydroscopic materials that are so hygroscopic that they are not only able to pull in water and incorporate it into their crystal, they're able to pull in so much water that they actually make a concentrated solution of themselves in the water they've harvested from the atmosphere. These are kind of annoying to work with, to say the least. These are called deliquescent. Yeah. So keep the lid on the bottle. Otherwise, it might dissolve itself. They are really annoying when that happens. But otherwise, have a wonderful day, and I'll see you in later videos.